Hey guys, if I'm being honest, I would say that limits is not a hot topic in AAHL. These types of exercises are not quite common. However, they do appear sometimes, occasionally, usually in exercises that involve Maclaurin series expansions. But that, of course, doesn't mean that you shouldn't know how to solve them. You should know how to solve every type of limit, and this is the purpose of this video, of this lesson. And another motivation behind this lesson, behind this video, is to not only talk about these techniques that we can use to solve these limits, but also L'Hopital's rule, which can be considered a technique as well. But we're gonna do it in two different ways, with and without L'Hopital's rule, because well, sometimes you can't use L'Hopital's rule, and other times using some algebraic method is actually better than using L'Hopital's rule. So let's get to these six limits. All right, so these are the six limits that are going to illustrate these six possible cases. One of them is very easy, it's very straightforward. The other five, they do require some sort of factoring technique or other technique. And for some of them, we can use L'Hopital's rule, as I was mentioning before. Now, do know that they're not in increasing order of difficulty. And before we even begin, let's talk about L'Hopital's rule so we can apply it after we solve these exercises without L'Hopital's rule. We can apply L'Hopital's rule in two specific indeterminate forms, which are 0 over 0 or infinity over infinity. And for these ones, L'Hopital's rule states that if you have two functions which are differentiable, and let's call these two functions f of x and g of x, and either, so one of the two, the limit of f of x as x approaches a and the limit of g of x as x approaches a, they're both equal to 0, or this is the second condition, the limit of f of x as x approaches a is positive or negative infinity, and the same thing happens to the limit of g of x. So in other words, we have 0 over 0 or infinity over infinity. This is where we can apply L'Hopital's rule, which is the limit as x approaches a of f of x over g of x. It is equal to the limit as x approaches a of f prime of x over g prime of x, the derivatives of f and g respectively. Now, one thing to be very careful here is not to use the quotient rule when applying L'Hopital's rule. These derivatives are the derivatives of these portions, the numerator and the denominator, separately. So that's why we have the limit of f prime over g prime. So these derivatives are the derivatives of f and g respectively, not using the quotient rule. And something else that's worth mentioning is that there are not only two types of indeterminate forms. However, these are the types in which we can use L'Hopital's rule. There are actually seven. The other five, they are 0 times infinity, infinity minus infinity, and the last three are 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. However, for these last five, we cannot use L'Hopital's rule directly. We gotta do some sort of manipulation. This is a little bit outside of the IB curriculum. However, there could be a way to build an exercise either for paper 3 or even for papers 1 and 2, the section B exercises, the longer ones, which could ask you to do some sort of manipulation, get to 0 over 0 or infinity over infinity so that you could use L'Hopital's rule. But I'm yet to see such a question. This is more college calculus. All right, so given that we talked about L'Hopital's rule already, let's get to these six exercises. The first thing you want to try is to plug in the x value, the limit for which x is approaching, into the function itself. And that already tells us which is the easiest one of these six limits. That will be the fourth one. On the fourth one, we can plug in x as 2 into the rational function. Why can we do that? Well, the function is not discontinuous at 2. It is discontinuous at 3. We can see that there's a vertical asymptote x equals 3. But that's not a problem because we're plugging in 2 as the x value. So we can just plug it in and find the limit. The function will be continuous. It is continuous when x is equal to 2. Therefore, the limit is the same as f of 2. So 4 times 2 plus 1 over 2 minus 3, also known as negative 9. So by substituting, we already got the correct answer. So let's move to a second example, a second type. We can see that in example number 1, we cannot plug in 5 as the x value because we're not only going to get 0 in the denominator, but also 0 in the numerator. So we have 0 over 0, which is an indeterminate form. That being the case, we can do it in two different ways, with or without L'Hopital's rule. We're going to do without first, which requires us to factor this quadratic. Using sum and product, we need to find two numbers that add up to negative 9, whose product is positive 20. And these are negative 4 and negative 5. The fact that trying to plug in 5 over here gives you a 0 should already tell you that x minus 5 is a factor. So we have x minus 4 times x minus 5 over x minus 5. And we can cancel out these x minus 5. So we have the limit as x approaches 5 of x minus 4. And we can substitute x by 5, which of course gives us 1. And we can call this technique a sum and product, or more broadly, factoring a quadratic. Now let me change the color here so we can do this using L'Hopital's rule. Using L'Hopital's rule, given that we have over here an indeterminate form 0 over 0, or the indeterminate form 0 over 0, we can say that this is the same as the limit as x approaches 5 of the derivative of the top 2x minus 9 over the derivative of the bottom, the denominator, which is 1. And we can plug in x as 5 now, or 5 as x, which gives us 2 times 5 minus 9, which is in fact equal to 1. Should we get the same answer? Absolutely. All right, so third exercise now, third type. What you can probably spot in number 2 is a difference of 2 squares, and now I'm talking about the numerator in this case. We have x squared minus 1 squared, and we all know that a squared minus b squared can be rewritten as a plus b times a minus b, meaning that this limit may become x minus 1 times x plus 1 over x plus 1, and we can cancel these terms and have, in the end, the limit as x approaches negative 1 of x minus 1, which is negative 1 minus 1, which is equal to negative 2. Now, something that I didn't actually mention in the beginning is that if you try to replace x by negative 1, you get an indeterminate form, which is 0 over 0. So that's why factoring was required. And this also shows that we can use L'Hopital's rule, which in this case will give us the limit as x approaches negative 1, the derivative of x squared minus 1, which is 2x, over the derivative of x plus 1, which is just 1. And right now we can replace x by negative 1, which gives us negative 2, the same answer, of course. Now, as the fourth example, we can tackle exercise number 3 here. And notice that in this case, the limit is for x approaching positive infinity. We have not 0 over 0 right now, but we do have another indeterminate form, which is infinity over infinity. Now, in this case, if you don't want to use L'Hopital's rule, you can and should factor out the highest power of x. So we can call this the highest power. And what I mean by that is we're going to factor out, in this case, x cubed from both the numerator and denominator. So we have x cubed times 4 minus 2 over x plus 2 over x cubed over x cubed times 7 minus 1 over x squared plus 1 over x cubed. Now, why do we do that? Well, we do that so we can, first of all, simplify these x cubed rewrite this limit as such. And by noticing that as x approaches infinity, all these four terms, they will all approach zero, given that we're dividing a integer or a constant by x or by x squared or by x cubed, which is a gigantic number. The only thing that we're going to have left is 4 over 7. And there you go. Now, something else that I didn't mention was the fact that both these powers, these highest powers of x, they're the same. They're both x cubed. For this technique to make sense, you gotta have polynomials in the numerator and denominator of the same degree. Because, well, if the polynomial in the numerator is of a higher degree, well, the limits is just gonna be either positive or negative infinity. Now, if the denominator has a higher degree, then the limit as x approaches infinity or negative infinity, it's just going to be zero. The main question about using L'Hopital in this case is not specifically how to differentiate these polynomials, obviously, because it's quite easy. However, one question that students always have is how many times can I use L'Hopital? Because, well, if you differentiate it once, you're still going to get infinity over infinity. And the answer for that is you use L'Hopital's rule as long as it makes sense. So as long as you still have infinity over infinity or 0 over 0, which is not the case for this specific limit. So let's apply L'Hopital multiple times. We have the derivative of 4x cubed minus 2x squared plus 2, which is 12x squared minus 4x over 21x squared minus 1. Given that we still have infinity over infinity, we're going to apply it again, 24x minus 4 over 42x, and apply it once more, which gives us 24 over 42, also known as 4 over 7. Now 4 down, 2 more to go. Now in example number 5, we have a root. So what we're going to try here, and by the way, if you try to replace x by 0, you do get an indeterminate form. Therefore, we need to find some sort of way to simplify something, right? So one of the strategies that we can use here is to try to rationalize. It can be either the denominator or the numerator. So in this case, we have a root in the numerator. So let's call this rationalize. We're going to multiply the top and the bottom by root of x plus 1, and by the same thing, of course, so we don't change the function, we're going to multiply it in the denominator as well, the denominator by it as well. So we have root x plus 1 times root x plus 1, which is x plus 1, plus root x plus 1, minus the same root, minus 1, and we can, of course, simplify these roots. And in the denominator, we have x times the root of x plus 1 inside this set of parentheses. So we can also simplify the negative 1 with a 1, so that in the numerator, the only thing that we have is x, which will finally be simplified with the x in the denominator as well, giving us the limit as x approaches 0 of 1 over x plus 1 plus 1. And at this point, we can substitute x by 0 because we don't have any indeterminate form anymore. So we have 1 over the root of 1 plus 1, also known as 1 over 2. Can we use L'Hopital over here? Yes, absolutely, we can. The derivative of root of x plus 1 minus 1 is 1 over 2 times the root of x plus 1 times the derivative of x plus 1, which is just 1, over the derivative of x, which is 1. And at this point, we can replace x by 0, which gives us 1 over 2 root of 1, which is, of course, 1 over 2. Let me squeeze this over here. And there we go. Now on to the last one, which is the least sexy one, the least important one. And that is because the factoring technique involved in this exercise is a difference or sum. In this case, it's a sum of 2 cubes, which is not a factoring technique that you need to memorize. We have a cubed plus b cubed. This can be rewritten as a plus b, a squared minus ab plus b squared, And also a cubed minus b cubed can be rewritten as a minus b times a squared plus ab plus b squared. Now you can, of course, also apply L'Hopital's rule for this example right here, but only once. You're only going to be required to apply it once. After the first iteration, you don't get 0 over 0 anymore. So given that this is the same as 2 cubed, we have x plus 2, x squared minus 2x plus 4. And we can cancel out the x plus 2's and replace the x's by negative 2. So we have 1 over 4 plus 4 plus 4, which is, of course, 1 over 12. But again, applying L'Hopital's rule, we have the limit as x approaches negative 2 of 1 over 3x squared, which is equal to 1 over, and right now we can replace x by negative 2, so 1 over 3 times negative 2 squared, which is 4, so 1 over 12. And we do get, of course, the same answer as before, and there you go. These are the 6 types of limits you need to know how to solve as an IB Math AA HL student.